Today we will discuss about introduction of antennas. Basically, we will learn about what is antennas and what are their parameters. So, what is an antenna? As you can see here, that an antenna is a passive structure. Passive structure means it doesn't store energy. It cannot amplify the signal. It is a passive component. It is not an active component. And antenna can be considered as a component which is generally used to convert electrical energy into electromagnetic energy or vice versa. So whenever you need to convert electrical energy into electromagnetic energy, you can use antenna, or whenever you need to convert electromagnetic energy into electromagnetic signal into electrical signal, then you can use antenna. When you need to convert electrical energy into electromagnetic wave, we call it transmitting antenna. And whenever you need to convert electromagnetic wave into electrical signal, then that kind of antenna will be called as receiving antenna. So this is receiving antenna and this is transmitting antenna. Transmitting antenna will be connected to the transmitter and receiving antenna will be connected to the receiver. So basically an antenna is a transducer. Transducers are those devices which convert one form of energy into another form of energy. Here antenna is acting as a transducer, means it is converting electrical energy into electromagnetic energy and electromagnetic energy into electrical energy. So whenever you need to convert signals from electrical domain to electromagnetic domain, you can use an antenna as a transducer. An electrical signal can be guided through a transmission line, while when you want to this signal be propagated in space, you need a transducer. That transducer will convert that electrical energy into electromagnetic energy, and that electromagnetic wave will be transmitted through space and will reach to the receiver using space. Here space is acting as a channel of transmission. Electrical signal, after converting into the electromagnetic energy, will propagate through space, travel a distance and reach to the receiving antenna, and on receiving antenna that signal will be again converted into the electrical energy and will be given back to the receiver circuitry. Now how this phenomena occurs, how this transformation of electrical energy into electromagnetic energy and electromagnetic energy into electrical energy happens, can be described using this diagram, which will be called as concept of radiation of electromagnetic waves from an antenna. So you can see here that here an alternating current is being generated, and this alternating current, after passing through this transmission line and this curved line, is converting into electromagnetic radiations, electromagnetic waves. So in this particular diagram, you can see that electrical energy is being converted into electromagnetic wave with the help of this structure. You can see here that from this particular point, the wire has been bent. Wire is bent, and you can see that this particular portion is responsible for conversion of electrical energy into electromagnetic wave. Before this, if there is a current in these two wires, then they will cancel each other. Their radiations will be cancelled by each other. However, when this wire will be bent at this particular point, after applying right hand rule, you can see that magnetic field due to current is not cancelling each other. Magnetic field due to current carrying wire at this particular moment will cancel each other, because if you will use right hand thumb rule, then magnetic field at this particular point will be inside due to this wire and outside due to this wire, and both will be cancelled out. So radiations in this particular region will be cancelled out. However, when you bend this wire like this, then the magnetic field generated due to current will not be exact 180 degree out of phase, and therefore resultant signal will not be cancelled out and electromagnetic wave will be formed. Similar to this, at the receiver end, this antenna will receive this electromagnetic wave and convert back into the electrical signal at the receiver signal. So this is the antenna function at the receiver side, and this is the antenna function at the transmitter side. Actually, what happens that when you apply right hand thumb rule, if this is a current carrying wire, and if you are applying right hand thumb rule, then you will put your thumb in this direction. You will put your thumb in this direction, and the direction of rotating fingers will give you direction of magnetic field. For example, at this particular point, direction of magnetic field will be into the board. If you are having another current carrying wire, then at this particular point, this direction of magnetic field due to this wire will be out of the board. So you can see that both the fields are equal and opposite. If both the currents are equal and opposite, if both the currents are equal, then fields will be equal and opposite. And in this kind of scenario, fields might get cancelled with each other, and due to this, field cancellation will take place in this region. While in this region, they will not be exactly out of phase, and therefore cancellation will not occur. So this is the phenomena of transmission of electrical signal into electromagnetic wave at the transmission at the transmitter side, and this is the phenomena of reception of electromagnetic wave at the receiver side. This concept is just reverse of the this concept. This is in transmitter side, and this is in the receiver side. Now, antennas can be classified in two broad categories. These broad categories are based on their structures, based on their geometries. You can see that there are two groups. One is called as wire antenna, and another is called as aperture antennas. All those antennas which are made of thin wires, thin conducting wires, thin conducting wires will come under wire antennas. For example, dipole antennas, loop antennas, Yagi-Uda antenna. They are made of thin conducting wire-like structures. You can see this is dipole antenna, this is loop antenna. Both are made of wire, so they will be called as wire antennas. On the other hand, aperture antennas are those antennas which have some area, which have some surface area. Conducting surface area will be there. If antenna is having conducting surface area, then that antenna will be part of aperture antennas. Aperture antennas are parabolic reflector antennas, horn antennas, microstrip antennas. You can see that all these antennas are having some conducting surfaces, and due to that conducting surface, these antennas are part of aperture antenna. Aperture antennas will carry some conducting surfaces in their designed geometry. For example, microstrip antenna, if you will talk about microstrip antenna, there are copper conducting copper areas on the top of the antenna, and that copper surface area is conducting surface area, and that's why it is the part of aperture antennas. Other examples of wire antennas are log periodic antenna. You can see here, this is log periodic antenna, this is Yagi antenna, this is the working of Yagi antenna. You can see that signals are coming at the conductors of Yagi antenna and being received, which has been shown by the diagram. This is another kind of wire antennas. You can see that thin parallel conducting wires are being used here, and these are log periodic antennas. And this is Yagi-Uda antenna with reflector. Here a reflector has been added to the circuitry, and this antenna is most famous antenna of old days, and you know about it. In this there are several parallel conducting wires which are being used for the transmission and reception of electromagnetic waves. This is another aperture antenna. You can see here that this is again carrying some reflector kind of structure, parabolic structure, and corner reflector. And this is having aperture, this is having aperture, and that's why they will be the part of aperture antennas. Other aperture antennas are reflector and pyramidal horn antennas. You can see this structure here. You can see that this is a parabolic reflector. How it works basically, electromagnetic waves will come parallelly and will be incident on this parabolic reflector. After reflection, they will all go to the focal point, and this device is at the focal point which will receive this incoming signal. In this way, parabolic reflector works. On the focal point of this parabolic reflector, there will be a receiver which will receive the signals coming from the space, coming from the air, and signals coming from the air will vertically be incident on the parabolic reflector. After reflection from the parabolic reflector, they will be received by the receiver at its focal point. You must remember that this is the focal point of this parabolic reflector. Similar to this, these two antennas are also working. Now, there is a theoretical concept of antenna, and that is called as isotropic antenna. Isotropic antenna does not exist practically, does not practically exist. It is a theoretical concept. Isotropic antenna is a point antenna. It is a point antenna which radiates equally in all directions. Radiates equally in all directions. If an antenna is radiating equally in all directions, then that antenna will be called as isotropic antenna. There is no such antenna which exists. This is currently existing, but it is a theoretical concept. An antenna which radiates equally in all directions will be called as isotropic antenna. And the basic purpose of this antenna is to just compare practical antennas. Performance of practical antenna will be evaluated by comparing the performance of practical antenna with isotropic antenna. The radiation pattern of isotropic antenna will be a sphere. A complete sphere will be the radiation pattern of isotropic antenna. Means isotropic antenna will radiate in such a way that its radiation will be in the form of a sphere. Means it will radiate equally in all directions. It is a hypothetical antenna. It does not exist practically. It does not exist in real life, and it is used to characterize the antenna parameters. It is a point source that occupies negligible space, has no directional preference, it radiates equally in all directions. Its pattern is simply a sphere. And therefore its beam area will be 4 pi steradian. Beam area is basically the area through which power of the antenna streams. Power of the antenna would stream through the beam area. Means the area through which antenna radiates will be called as beam area. And for a isotropic antenna, beam area is a complete sphere, and its beam area will be given by 4 pi steradian. Steradian is the unit of angle represented in 3D. In 2D we use radian. In 3D we use steradian. When an angle will be represented in 3D, we will represent in steradians. 1 steradian equals to 1 square steradian. 1 radian into 1 radian will be equal to 1 steradian. So for isotropic antenna, beam area will be 4 pi steradian, because the area of sphere is 4 pi r square, and the product of r square the constant term with the r square will be called as beam area, and it is 4 pi. Beam area is the angle through which power of the antenna radiates. Now, antenna parameters. Any antenna has some parameters over which their evaluation is done, And these parameters are known as antenna efficiency, directivity, gain, solid angle, radiation intensity, radiation pattern, side lobes, half power beamwidth, and uh, far field region. So one by one we will discuss about it. So first we will come to the antenna parameter, antenna efficiency. What is efficiency in terms of antenna? It is basically when what is the function of antenna? Antenna basically converts electrical energy into electromagnetic wave. So whatever input we are giving to the antenna, some of the energy is being radiated into the space, and some of the energy is being lost due to losses inside the antenna. So antenna efficiency can be defined as it is the ratio of power radiated from the antenna. It is the ratio of power radiated from antenna, to the total power supplied to the antenna, total power fed to the antenna, power radiated from antenna to the total power, radiated from antenna to the total power fed to the antenna. Antenna efficiency is the ratio of power radiated from the antenna to the total power supplied to the antenna. There is one other term in terms of efficiency, and that is called as radiation efficiency. Radiation efficiency. This term does not include losses, excludes losses due to mismatch. So when you will define radiation efficiency, you will write that radiation efficiency is the ratio of power radiated divided by power accepted by antenna. Power radiated by antenna divided by power accepted by antenna. Power accepted by antenna. So antenna efficiency includes losses due to mismatch, while radiation efficiency does not include losses due to mismatch. If you will exclude losses, then efficiency will be called as radiation efficiency. Radiation efficiency is the ratio of power radiated by the antenna to the power accepted by antenna. It excludes losses due to mismatch. Antenna efficiency includes losses due to mismatch. Antenna efficiency is defined as the power radiated from the antenna to the total power supplied to the antenna. Total power supplied includes losses due to mismatch. Whenever you supply power to an antenna for radiation, most of the power will be radiated, but certain portion of the power will be reflected back towards the input side due to mismatch losses, due to reflection coefficient, due to mismatch at the input terminal. Some of the power will be returned back towards the input side. So that mismatch loss will be included in case of antenna efficiency, and that mismatch loss will not be included when you will talk about radiation efficiency. Radiation efficiency excludes losses due to mismatch, right? While antenna efficiency includes losses due to mismatch. So antenna efficiency is the basically ratio of power radiated from the antenna to the total power supplied to the antenna, while radiation efficiency is the power radiated from the antenna to the power accepted by antenna. Means if you are supplying 10 watt power, and if antenna is actually receiving 8 watt, means 2 watt has been lost due to mismatch loss. 8 watt will be radiated into will be used for radiation. So that 8 watt will be called as power accepted by antenna. There is a term power accepted by antenna. Now the next parameter is directivity D or gain G. An antenna is defined based on their gain and directivity. There are two terms, gain and directivity. Here also gain includes losses due to mismatch, while directivity excludes losses due to mismatch. There are two terms, both are almost equal. For a lossless antenna, directivity will be equal to gain. For a lossless antenna, directivity will be equal to gain. If losses will be included, then these two will be different. But if losses are zero, if there is no loss, then D will be equal to G. D is known as directivity and G is known as gain. It is basically a definition with respect to isotropic antenna. it is defined as it is the ratio of power radiated by practical antenna, power radiated by practical antenna in a particular direction to that of power radiated by isotropic antenna in that direction, considering that equal power is being given to the practical antenna as well as isotropic antenna. Means suppose if you have an antenna and you want to calculate its gain, you will calculate its power in the direction of maximum radiation, and after that same power is being fed to the isotropic antenna, and again radiation intensity will be calculated at the in the same direction, and the ratio of these two terms will be called as gain. Gain is the ratio of power radiated by the given antenna in a particular direction divided by power radiated by the isotropic antenna in that direction. Radiation intensity of given antenna in a particular direction divided by radiation intensity of isotropic antenna for the same input power will be called as gain. And if there are losses, then gain and directivity will be different. And if there is no loss, if antenna is lossless, then gain and directivity will be equal. Gain and directivity are related with G equals to antenna efficiency into directivity. Gain equals to efficiency into directivity. If you will multiply efficiency in the directivity, you will get gain. So you can see here that antenna efficiency is basically power radiated from the antenna divided by total power fed to the antenna. It includes losses due to mismatch, and if you are multiplying this efficiency with the directivity, you will get gain. Now the next term is solid angle, also called as beam area, and radiation intensity is another parameter. So what is solid angle? Solid angle is the angle through which power radiated from an antenna streams. Means whatever 3D angle is being used for radiation of power by an antenna, that 3D angle will be called as solid angle. It is measured in steradian, and that angle is also called as beam area, represented by ohm A. While radiation intensity is another term. Radiation intensity is the power radiated per unit solid angle. Power per unit solid angle will be called as radiation intensity, while the total angle through which power is being streamed from an antenna, that angle will be called as solid angle of antenna or beam area of the antenna. The next parameter is radiation pattern. Radiation pattern can be considered as it is a graphical representation of behavior of radiation of an antenna. It is a three-dimensional or two-dimensional pattern. It represents in what way the power is being transmitted from an antenna. The radiation pattern of antenna is a graphical representation of radiated power in the space, and it consists of major lobes as well as side lobes. Major lobes and minor lobes. Minor lobes are in the form of side lobes and back lobes. And there is a term normalized power. Normalized power is the power which has been divided by maximum power. And half power beamwidth is another term. Half power beamwidth is the angle formed by the half power points of the radiation pattern. If antenna is radiating in a particular direction, then half power points can be evaluated, and if you will draw lines from those half power points to the antenna, there will be some solid angle, and that solid angle will be called as half power beamwidth. At half power beamwidth, antenna power is half. I have already told you that antenna efficiency is the ratio of power radiated from the antenna to the power supplied to the antenna. Antenna terminal power actually radiated divided by power put into the antenna. This is called efficiency. Power radiated divided by power supplied, power put into the antenna. And radiation efficiency is the efficiency excluding the losses due to mismatch. Antenna efficiency includes losses due to mismatch. Now, radiation in an antenna is caused by radiation resistance, which can only be measured as part of total resistance, including loss resistance. Here gain and directivity has been related. You can see that gain is you can achieve gain. You can get gain parameter by multiplying antenna efficiency with the directivity. Directivity is the gain of antenna excluding losses. If you will include losses, then that will be called gain. If you will exclude losses, that will be called as directivity. So if losses due to mismatch is 0, then G will be equal to D, and if there are losses in practical antennas, certainly there will be losses. So if you know the directivity, you can calculate gain by just multiplying efficiency with the directivity. This is the diagram which is representing isotropic antenna. You can see here that isotropic antenna, this is isotropic antenna, point antenna. It is radiating equally in all directions, and its radiation pattern is in the form of sphere. However, practical antennas radiate maximum in one direction. You can see this is practical antenna, it is radiating maximum in one direction. When you will compare this radiation with the radiation of the isotropic antenna for the same input power, then that comparison will be called as gain. The ratio of power radiated in desired direction of the practical antenna to that of ratio of the power radiated in that direction by isotropic antenna will be called as gain. Directivity is just another parameter which excludes losses due to mismatch. Gain and directivity is equals to eta D, as I have already told you, where eta is the antenna efficiency. Now, to understand the beam area or beam solid angle, you must know spherical coordinate. Spherical coordinate has three parameters: radius r of sphere, radius r of sphere, angle theta with the z axis, which forms a cone, angle theta with z axis of this cone, and phi plane, angle phi of the phi plane. There are three parameters: r, theta, and phi. You can see that if you want to move in phi direction, if you want to move in this direction, if you want to move in this direction, that direction has been represented in this diagram like this. Then this is the direction of phi plane. Phi plane is moving in this direction. So if you want to calculate an arc, suppose this is the arc, and if you want to calculate this length, then you have to calculate the radius, this length, and angle, this length. Arc will be equal to radius into angle. This is d phi, and this is radius. Then this radius into d phi will be equal to this arc. So if you want to calculate arc in phi plane, then you will multiply this radius with the d phi. And if you want to calculate arc in z plane, in theta direction, then here radius is this, and arc will be this one, and this is represented by d theta. So this radius, this length into this angle, this length into this angle is d theta. This radius into this displacement in angle will give rise to this arc. So if you want to calculate this arc, then you will multiply radius with d theta. If you want to calculate this arc, you will multiply radius with d phi. So if you know the radius in this plane, then you need to find out component of this radius on this plane. That will be equal to r sin theta. That component of this radius, component of this r in this direction will be equal to r sin theta. And if you want to calculate this arc, then you will multiply r sin theta into d phi. So r sin theta will be into d phi will be the arc in this direction, and r into d theta will be arc in this direction. If you want to calculate differential area on the surface of a sphere, for example, in this particular diagram, you can see if you want to calculate a differential area on the surface of the sphere, this is the differential surface area. If you want to calculate this area, then you need to calculate this arc and this arc, and after multiplying these two, you will get area. So this arc is in the direction of phi, and this arc is in the direction of theta. So this will be equal to r into d theta, and this will be equal to r sin theta into d phi, radius into angular displacement will be equal to arc. After calculating, evaluating two arcs, if you will multiply these two, you will get area of this particular differential element of the sphere on the surface of the sphere. This differential element exists. If you want to calculate area of this differential element, you need to evaluate this arc and this arc, and after multiplying the lengths of these two arcs, you will get the differential area of the differential area which exists on the top of the sphere. So I have told you that this is S1, S1 is r d theta, and this is S2, S2 is r sin theta into d phi, r sin theta into d phi, and r into d theta will give rise to this particular differential area. So differential area will be S1 into S2, and it will be equal to r square sin theta d phi. This term sin theta d phi is called as beam area and is represented by d ohm. You can see here r square equals to d ohm. This d ohm is defined as solid angle, also called as beam area. So for an isotropic antenna, if antenna is isotropic, then obviously the surface area of isotropic antenna is given by 4 pi r square. Multiplication of r square is 4 pi, so d ohm is equals to 4 pi. So for an isotropic antenna, solid angle of its sphere will be 4 pi, and therefore 4 pi steradian will be the solid angle of a isotropic antenna. Isotropic radiator will have a solid angle of 4 pi steradian, or you can say that beam area will be 4 pi steradian. Beam area is the surface area through which entire power of the antenna streams. Entire power of the antenna would stream. For an isotropic antenna, radiation is equal in all directions. So 4 pi steradian will be the beam area of the isotropic antenna. Now radiation intensity is the, as you can see, radiation intensity is nothing but it is the ratio of power density divided by solid angle. So power density per unit solid angle will be called as radiation intensity. It is defined in terms of Poynting vector as r square PR. PR is the Poynting vector, and it is represented by 1 by 2 real part of E cross H complex. E cross H is the electromagnetic wave. You know that direction of if electric field is in this direction, magnetic field is in this direction, then electromagnetic wave will propagate in this direction, and that is called E cross H, perpendicular to both electric and magnetic field. Electromagnetic wave propagates. So this is the flow of power. If electric field is in this direction, and magnetic field is in this direction, then direction of propagation of electromagnetic wave will be in this direction, and this is called Poynting vector P. So radiation intensity in terms of Poynting vector has been given here. Radiation intensity is the power per unit angle. If you will multiply radiation intensity with the solid angle, you will get radiated power. So this is the relation between angle, radiation intensity, and total power radiated. Power radiated is equals to radiated power, radiation intensity into angle, because radiation intensity is the power radiated per unit solid angle, and if you will multiply power radiated per unit solid angle with the angle, total angle, you will get power radiated. Now radiation pattern. Radiation pattern, you can see here, this is the radiation pattern. It is basically representing how your antenna is radiating in the space. This is the major lobe. This is called major lobe, and this will be called as side lobes. Side lobes have less energy as compared to major lobe or main lobe. It basically represents variation of amplitude of radiation as a function of direction. It is basically variation of amplitude of radiation. Amplitude of radiation means how much power is being radiated in a particular direction. The magnitude of the radiation with the direction, if you will plot, you will get radiation pattern. It can be a 3D, it can be a 2D. There is another term called as total solid angle. Total solid angle can be evaluated by using pencil beam. Pencil beam can be understood like this. This is the main lobe. If you draw a cone like this, then this cone will be called as pencil beam because it looks like a pencil, so it will be called as pencil beam. The angle between these two sides of the pencil beam will be called as total solid angle. As you can see, if you change the radiation pattern beam of an antenna into a pencil beam shape, if you change the radiation pattern into pencil beam shape, and then the equivalent solid angle will be called as total solid angle, and mathematically it is represented by um, power uh, integrated around the solid angle. This is the radiation pattern view in another way. This is the main lobe and these are the side lobes. You can see that power of the side lobes are lower than the, and this is the main lobe, this is the side lobe. Graphical representation of power radiated is actually represented by radiation pattern. Now there are two terms, half power beam width and first null beam width. Half power beam width are the half power points. This is the main lobe. You can see here that antenna is radiating in this direction. Mainly this is the major lobe and these are the side lobes. If you draw a line from half power points of this main lobe and connect it to the antenna, then the angle between these two lines will be called as half power beam width. Half power beam width is angular distance between half power points. While if you will look at this line is the line where there is no radiation. The zone where there is no radiation is called as null. The no radiation area is called as null. And if that null is near the main lobe, that null will be called as first null. And so this is the first null and this is the first null. And angle between these two first nulls will be called as first null beam width. First null beam width, F and BW. Angle between first nulls will be called as first null beam width. Now, dipole antenna pattern you can see here. It is of donut shape. Donut shape means in the center there will be no radiation and all around there will be radiation. In the center there is no radiation. These are opposite points, and there is no radiation, and all other points have radiation. This is called donut shape. Dipole antenna means di means two, and pole means conducting wires. So this is the one pole and this is another pole, and due to these two poles it will be called as dipole antenna. If you change the shape of these two poles like triangular shape, it will be called as Bouty dipole. And similarly, if you will fold and connect this but the width should not be very high, then that will be called as folded dipole. And similarly, if the area covered by the loop is large, then that will be called as loop antenna. So depending upon the shape, there are different names: dipole antenna, Bouty dipole antenna, folded dipole antenna, and loop antenna. All these are wire antennas. Side lobes are undesired lobes. Side lobes are basically undesired lobes. They are mostly in unwanted directions. So and has less power than main lobe. Antenna sometimes show side lobes in the radiation pattern. Side lobes are peaks in gain other than the main lobe. Main lobe is the main direction in which we want radiation. Other than main lobe, there are some radiations, and those radiations will form side lobes. Side lobes as well as back lobes. Both these lobes are not desired normally. In case of radar communication, this side lobes is very dangerous because it can give wrong results while tracking the objects. So in 3D geometry, you can see here these are the side lobes, and these two are main lobe. In this case, this is the main lobe. This is the main lobe. This is the side lobe. This is the side lobe, and this is the back lobe. These are the side lobes, and this is the back lobe. The side lobe magnitude should not exceed -20 dB. -20, it should be less than -20 dB for good performance. Now again, directivity and gain. You know that directivity and gain are calculated with respect to isotropic antenna. The ratio of radiation intensity in a particular direction divided by the radiation intensity of isotropic antenna in that direction will also be can also be called as maximum radiation direction divided by that power averaged over all the directions. So directivity can be defined as the maximum power divided by that power averaged equally over all directions will give rise to directivity. If lossless antenna is there, then directivity and gain both will be equal. Similarly, maximum radiation intensity divided by radiation intensity averaged over all the directions for a particular power will give rise to directivity. And directivity and gain are equal if antenna does not have mismatch loss. This is the mathematical representation of gain and directivity again. You can define directivity and gain. Power, total power, power radiated in particular direction divided by power averaged in all directions, and similarly this expression will come. This is again directivity. Directivity have been here. Directivity have been defined in respect with respect to beam area, and beam area can be evaluated by multiplying the two diameters of this circle. You can see that this is the main lobe, and in the main lobe there are two triangles. Two triangles. One is this one, and another one is this one. Both are at 90 degree. If you evaluate this distance and this distance in angular form and multiply this, you will get the beam area. Beam area is basically the area of this circle, and the area of this circle is around approximately equal to the multiplication of two diameters. So that is defined by beta fz into beta yz, and you will get omega a, and after that you can get directivity. Far field. There is another term called far field. The distance at which the field transmitted by an antenna can be approximated to a plane wave. Means when an antenna radiates, it's normally radiates in spherical form, and the wave front will be of spherical nature. But after some time, that spherical wave front will be approximated into the plane wave. That distance will be called as far field distance, and it is represented by RFF, far field distance, and given by 2d square by lambda, where d is the largest dimension of the antenna. Largest physical dimension of the antenna is d, and lambda is the wavelength of radiation. You can calculate the far field distance. Now polarization. Polarization is basically orientation of electric field. Orientation of electric field. If electric field is vertical, then we will call it vertical polarized wave. If electric field is horizontal, then we will call that horizontally polarized wave. And if electric field is moving circular, then we will call that circularly polarized wave. Circularly polarized wave is of two types: right hand circular polarization and left hand circular polarization. Means if the orientation of electric field is in anti-clockwise direction, then we will call that right hand circular polarization. If orientation of electric field is in clockwise direction, then that will be called as left hand circular polarization. The orientation of electric field will give rise to the RSCP and LSCP. If electric field is orienting in clockwise direction, that will be called as LSCP. If electric field orientation is in anti-clockwise direction, then that will be called as RSCP. Now antenna array. If multiple antennas are being used to enhance the performance, then that will be called as pattern multiplication, and it increases the performance of antenna. And that concept of using multiple antennas to enhance the performance will be called as antenna arrays. This is the radiation pattern of antenna. It was all about today's lecture.